Okay, hello everyone. What we're going to do now is we're going to move on from differentiation and we're going to look at integration. Now before we go and do that, let's just go ahead and get an idea of what the relationship is between differentiation and integration. Now when we talked about differentiation, we talked about taking a function that we have and differentiating it to come up with what we call f prime of x. Now what did that give us? That of course gave us the instantaneous rate of change, and based upon that we could analyze functions and we could do all different types of applications. Now what we're going to do is we're going to take that information and keep that in your mind. What we're going to do is we're going to move on to what is called integration or anti-differentiation. Now just in a nutshell, basically what's happening with integration is that you're given a function, and let's just say for example it's f prime of x. Through the process of integration, you are actually going to be able to come up with the original function, or f of x. So notice that with differentiation, you went from f of x to f prime of x. From integration to anti-differentiate, you actually go from f prime of x to f of x. So hopefully you can just kind of get an idea, well, those are actually inverse operations of each other then. And that is true. But we have to be careful because there are actually two different interpretations of integration. And we need to go ahead and talk about them at this time. There are two things called the indefinite, one is called the indefinite integral, the other is called the definite integral. Now, of course, this notation is probably the first time that you've seen this, but this is what the integral looks like, or the process of integration, and what the results will yield. So this symbol right here, which looks like a very elongated S, actually represents integration. And it is called the integral symbol. So what we're going to say then is that if we integrate f prime of x d of x, then what we're going to be doing, what we're doing is what we're finding is an indefinite integral, and what this yields is a function. Now you also have something called a definite integral, and notice that the slight change with this one is that this has an x is equal to n and x is equal to b at the top and at the bottom of this elongated s. Notice that I just wrote f of x, d of x, and this yields a number. So the indefinite integral is yielding a function, the definite integral is yielding a number. Okay? Now what we're going to have to do is let's go ahead and get an idea of what this actually represents and how all of this links together. So what we're going to focus on first is the definite integral. So here you go. The definite integral, again, is going to be yielding a number. Now, what does that number represent? Let's just go ahead and take a look at an example. Here is a definite integral for us. It says the integral from x is equal to 1 to x is equal to 3 of 1 plus x d of x. Now, the x equals 1 right here, that is going to be called the lower bound. The x is equal to 3, which is right here, is going to be called the upper bound. F of x is 1 plus x, and the variable of integration is d of x, or just x. Okay? Now what I did is I went ahead and I drew this. F of x equals 1 plus x. Here's the graph of that function. Now notice that with the green lines, I've actually included the lower bound and the upper bound. So the lower bound was x is equal to 1 right here. The upper bound was x is equal to 3, which is right there. Okay, so what this actually provides us again was with a number. What does that number actually represent? That number actually represents the area. Okay? The area that is bounded by the curve, the upper and lower bounds, as well as the x-axis. Okay, now I just wrote this here because I want to make sure that we all recognize exactly which area is being calculated. So I'm going to put these little black dots in the area that is actually going to be represented by this particular definite integral. So here we go. Okay, there you go. So if you can calculate that area, then you've actually been able to calculate this definite integral. Now, of course, we're not going through the process right now of actually integrating, but we want to get a conceptual idea of what a definite integral actually provides us with. So, if I say that the definite integral from x is equal to 1 to x is equal to 3 of 1 plus x d of x, that really represents, if we look at it from a graphical perspective, the area of this particular trapezoid. Okay, so we know that the formula for a trapezoid is just going to be 1/2 times the quantity base 1 plus base 2 times it by the height. So let's just take a look. We have 1/2. This will be one of the bases, right? Because these two are the parallel sides, right? This is the parallel side and this is the parallel side, so that's the bases. So the basis here is going to be 2 plus this base here is going to have a length of 4 times it by the height, and the height is here. So we have a height of 2. So if we go ahead and calculate that, then the area of the trapezoid is 6, and that is actually the value that would be given to you if you were to integrate this particular definite integral. Okay, so hopefully that gives us an idea of what's actually happening here. Now, of course, when we get in class, we're going to have to talk a little bit more specifically about how this actually comes about. But that's going to take a little bit more time, so we'll do it then. Now, the one thing that we're also going to need to be able to do is to be able to calculate the definite integral using your calculator. So, how do you calculate a definite integral on your graphic display calculator? And how is it that the number can be negative? If we're talking about area, how is it that area can actually be negative? And again, we'll go ahead and discuss that in class. But hopefully this has given you a very broad overview of what's actually happening with regards to integration and how it connects to differentiation as an inverse operation. Alright, so we'll go ahead and take a look at this and discuss this in class. Go ahead and read through the section and we'll see how we do. Alright, good luck. Bye-bye.